recording. So we'll get as many of the techniques in before the reading break, and then we'll continue techniques after. So there's some questions on the assignment 3 that's due in March sometime after the reading break. But I probably won't get to improper integrals and stuff like that, so don't worry, we'll be talking about it after reading break. Today I'll just finish, roughly speaking, the different techniques of integration that we have. So last time we were doing trigonometric substitution, and just before that we did trigonometric integrals. So trigonometric integrals means that we have these 3 cases essentially, and then there's 4 subcases in each one. But we have integrals of sine and cosine powers, integrals of secant and tan powers, and then integrals of cosecant and cotan powers. Cosecant and cotan and secant and tangent techniques are awfully similar because the derivatives are the same, and then the sine ones are slightly different. Once we do that, the whole point is we now get integrals that involve these things: x squared plus a squared, square root x squared minus a squared, or square root x a squared minus x squared. There's technically 4 cases again, but a squared plus x squared is the same thing as x squared plus a squared. So those are the 4 cases of adding and subtracting the a and the x squared. Once I have these, what we want to see is, what I'm seeing there is I want to get rid of that. So I want to see the trigonometric Pythagorean identity which matches that one. This one, I see tan a squared tan squared theta plus a squared equals a squared secant squared theta. That's what you want to see, so that you can pull the a out. And it's a little harder with the a in there. It's easier with the 1 formula at first because then the a is not in there, but that's what you're trying to see. For the other one, we know that a squared tan squared theta, if I move it to the other side, is exactly equal to technology. This is equal to a squared secant squared theta minus a squared. When you get back to the a out, and then it's gonna, the square roots will go away. And then in this one, we're gonna have a squared cos squared theta is equal to a squared, or sorry, minus a squared sine squared theta. And then that'll allow us to get rid of, but that's what I'm really trying to see every time, is the slightly altered, for our purposes, Pythagorean identities for each of these cases. And then, for example, if I have the square root of x squared plus a squared, this is the case that also happens in partial fraction decomposition. Which we'll see hopefully today, is when I have something like that, I want to let x equal a tan theta, because then x squared is equal to a squared tan squared theta, and we get the square root of x squared plus a squared is exactly equal to the square root of a squared tan squared theta plus a squared. This is what we're noticing every time. This is the square root of a squared times tan squared theta plus 1. By the Pythagorean identity, tan squared theta plus 1 is secant squared theta. So this is the square root of a squared secant squared theta, which is absolute value, but in the region that we're considering, we're going to make this positive. So this will be a secant theta. So we got rid of the radical. This is how we're going to, the trigonometric substitution is a way of getting rid of, if we have a function which is actually rational in x and the square root of x squared plus a squared now, where that means it just has powers of those types of things in there. If I make this substitution, I can turn it into a function which is now, if I'm using this substitution, this also says dx is equal to a secant squared theta d theta. So now what we're really saying is, anytime I have any integral which involves a rational function in these two variables, x's and square roots of these guys, then I can use this substitution, which is an inverse substitution, a tan theta. And we're going to get what? This integral in its most general form is going to be that rational function in x. What was x? X was a tan theta. What's the square root of x squared plus a squared? A secant theta. So rational or products, possibly a division sign, but product of secants and tans. And then times what's my differential? My differential is a secant squared theta d theta. This is the idea of how we use these trigonometric substitutions. The trigonometric substitution, when it's a rational function in x and the square root of x squared plus a squared, if I make the substitution a tan theta is x, then I get a rational function in products of secants and tans, which we had a whole technique on how to deal with. This is the strategy to get us out of that. So example 1 today. We have, let's do, so this is exactly what they're saying. If r of x, y is equal to y over x, if that's my function, a rational in x and y, then what I would do is if I had a rational function in x and the square root of x squared plus, let's do 4 or 2 squared, is going to equal what? I put x squared plus 4 over x. I had y here, and I have the y coordinate here. So it says put y on the top, and it says put x on the bottom. So that's what I did. So now, if I take that, what if I want to integrate that function? Let's do, sorry, squared. So this is what I mean by the rational function in x square root x squared plus 4. So now what's the integral of r of x square root x squared plus 4 dx? This is equal to the integral of what you're used to seeing as in less abstract. That's what we're talking about. In general, this is how we see the general technique of trigonometric substitution will work on these rational type functions if the variables are x and square root of those guys. Now you see what I'm trying to do. If I'm trying to integrate this thing, what am I going to do? I'm going to let x equal 2 tan theta. Then immediately my differential dx is 2 secant squared theta d theta. And x squared is 4 tan squared theta. And the square root of x squared plus 4 is equal to 2 secant theta. It'll get faster, but you can do this, put the substitution of the x in there with the square root. The whole point of this is to get rid of the square root on there in this rational, in this radical. So now that I have those things of my trigonometric substitution, I make that trigonometric substitution, and we get the integral of the square root of x squared plus 4 over x squared dx is now equal to, with our substitution, this was the integral of 2 secant theta was the top, dx is 2 secant squared theta d theta, and this is over 4 tan squared theta. Let's clean that up. It looks like the 2's cancel, first of all. And then now we have trigonometry. Because they gave us division, it won't be just quite products of secant and tan. We're going to get something slightly different. This ends up simplifying to the integral of secant theta times cosecant squared theta d theta. the cos, when you write everything out, the coses cancel and you're just left with two signs on the bottom, which is 1 over sine squared or cosecant squared. Now you ask yourself, what do I do? And now you have to start, this is why I picked this one, because it stumped me the first time I looked at it. I'm like, oh, because the division, by divided by x squared, we didn't just get products of secants and tans, we got division by tan squared. And so now it gave us secants and cosecants. So sometimes when you're looking at an integral and you're stuck, every time we stop and we're in the fray, now I've done trigonometric substitution, but now when I've done the trigonometric substitution, it gave me something else. And it's now a secant with a cosecant squared. Nobody said anything about this technique. So what am I going to do? I want to see integration by parts. I want to see a dv. What do you know how to integrate? And what do I know how to differentiate? I know how to differentiate secant, and I know how to integrate cosecant squared because the derivative of cotan is negative cosecant squared. So I'm going to let u equal secant theta, du is equal to secant theta tan theta d theta, dv is equal to cosecant squared theta d theta. So v is equal to negative cotan theta. Therefore, by integration by parts, this integral now becomes equal to u times v negative secant theta cotan theta minus minus, so plus the integral of cotan theta secant theta tan theta d theta v du. Cotan and tan cancel each other. So this is equal to negative secant theta cotan theta plus the integral of secant theta d theta. And now using clever trigonometric or substitution rule, you multiply by secant plus tan on the top and the bottom, and you get that this is negative secant theta cotan theta plus the natural log of the absolute value of secant theta plus tan theta plus c. And now are we done? We have to go back to our original triangle business. So what do we have? This is equal to, and we'll see how we did this in a second. I have an angle theta. It told me that tan theta, 2 tan theta equals x, or tan theta equals x over 2, which is opposite over adjacent. So this is opposite, this is adjacent, and this guy is going to be x squared plus 4. Now I just build from that triangle. Now I just build, what do I need? I need secant. So that says immediately cotan theta is going to be 2 over x, and secant theta cos is going to be the square root of x squared plus 4 over 2. So what do we get? Our integral is equal to secant was, so negative the square root of x squared plus 4 over 2 times cotan, which is 2 over x. These cancel nicely. Plus the natural log of secant was the square root of x squared plus 4 over 2 plus tan theta, which is x over 2 plus c. You can leave it like that. There's no point simplifying, but that's our antiderivative. So this is trigonometric substitution. You're going to want to go through and do a few of them, especially ones that have division in them, because you get slightly different integrals than just products of secant and cotangent. So you still have to know sometimes all your other techniques. Every time I do a technique, I say, now what's my integral look like, and what am I going to use next? And sometimes when they give them to you, you're going to have to use 4 different techniques: regular substitution, then trigonometric substitution, and partial fraction decomposition, then another regular substitution, and then you get your answer, and you have to backtrack to all the variables. So this can get out of hand real fast. I believe that's all the trigonometric cases. So we want to do, let's do partial fractions, because it's the day before our I'm just trying to pick nice partial fraction decomposition. So this is, I don't know where we were on. Substitution rule, integration by parts, trigonometric integrals, trigonometric substitution, partial fraction decomposition. So what are we trying to do? We're trying to integrate all rational functions. So what's a proper rational function? R of x is equal to P of x or A of x over B of x. Let's do A over B. So in my lecture notes, I go over this in many, many details pages, but the problem is the first several pages of this section of my lecture notes just deals with how to factor polynomials and do all this kind of stuff because it's a non-trivial task in general. So for us, what do we mean by proper? Proper means that R of x is proper if the degree of the numerator of the top is strictly less than the degree of the denominator. This is when we have proper. So you want proper in the decomposition. So step one, when I do partial fraction decomposition, and in most of the books they've already done this because they don't want to talk about long division, but it has to be proper. If not proper, create proper using long division of polynomials. So what do I mean by that? Well, if you have, so as an example, numbers first. If I have 7 over 3 and I want to know what the integer part is and the fractional part, then they say, okay, you do long division and you divide 3 into 7. This is the way I was trained to write it, like that. You write it like this guy. And then I ask myself, I'm going to get a quotient and a remainder. What do I have to multiply? I have to multiply by 2. I get a 6. I subtract, I get a 1. When the 1 is less than the 3, we can stop. And this tells us that we have that I can write 7 equals 2 times 3 plus a remainder of 1. This is using the division algorithm. But why is that good? Now divide both sides by 3. Okay, I will. And this gives me cancel, cancel. And so writing this as the quotient and remainder tells me that 7 over 3 is 2 plus 1/3. And then in school, for some reason, which I disagree to this day still, I was just doing it with my daughter, they say write it as a mixed fraction so that it's baking crap. But 2 and 1/3, the and means plus. So you're just adding. You're like, why are you talking about this? Well, with the polynomials, the technique's going to be the same. I have A of x over B of x. So what I'm going to do is I'm going to divide, and we'll do possibly one in one of my examples just to show you the long division. So I'm going to do that. And then a long story short, however we do this, we get a quotient and then we subtract, and then eventually you get a remainder. And when you get, in this case, when you get the degree of R is strictly less than the degree of B, which means proper, this means we can stop. And that tells us what? I can write A of x as Q of x times B of x plus a remainder, just like I did with the numbers. And what is that good for? Because now I can divide by a, and that says a of x over b of x is equal to q of x plus r of x over b of x. So what we're doing here is we've got three pieces now. This is improper. Using the long division, I've now created a polynomial plus, and now this is proper. So if you have improper, you can always create proper from doing long division, and then you're going to get a polynomial plus an improper. And if we wanted, the whole goal is to integrate these things. This says now that the integral of that improper function is equal to the integral of a polynomial, which is just the power rule. We're done with that one. That one's done because we know how to integrate polynomials, and plus now a proper rational function. So that was my long rant for basically the first step in partial fractions always is make sure it's proper. You can't do this technique if the degree is larger or the same on the top as the bottom. You have to make sure it's strictly less. Usually the books give you problems that are already cooked up like that, but sometimes they'll throw you that when you're like, what should I do with this one? Like the integral of x squared over x squared plus 1 dx. This is improper because the degree of x squared is equal to 2, which is equal to the degree of x squared plus 1. So what do? Either I use long division or I use a clever trick. Using long division does the same thing, but if I write this as x squared plus 1 minus 1, I just add 0 on the top and the bottom. And then push this through, which is essentially this just me being lazy today because it's right before we get a week off finally. But this is now the integral of what? We just have 1 dx minus the integral of 1 over x squared plus 1 dx, which is now just a polynomial plus a proper rational function now, which is just x minus, and now this is why we're going to need this guy. This one is, what's the derivative of arctan? 1 over x squared plus 1. So what's the integral of this? Arctan x plus c. So this is improper to start off with. But what I do is I make it into a polynomial plus a proper rational function, and then I can integrate it, is the idea. This one was already ready for partial fractions. So now what the heck is partial fraction decomposition? So given a proper rational function, long story short, we're going to make certain guesses for making all of the terms. We're going to have products on the bottom. We're going to factor our b of x into all of its linear and irreducible quadratics, but now they're multiplied together. I'm trying to integrate that. What partial fractions is going to do is take all the multiplications and string it into a bunch of pluses where there's only just one of each term. And then integrating that thing that had all the multiplications is going to be integrating individual terms where we can add and integrate and separate them all individually. So the idea is we're going to r of x, which is a of x over b of x. If we try to integrate this, we use partial fractions. To separate all the linear and irreducible quadratic powers from products to sums. Integrating all the, so what do we mean by that? I'll go through that the guesses are in each case. So if you have, there's actually only 2 cases, but I'll go through them in 4 cases. So the first case is if you just have 1 over x minus a in the product of your denominator, then what we're going to do is we're going to guess an a over x minus a. It's going to be our guess for that part. You'll see what we mean in a second when I pull this all together. If I have x minus a to some power now, to the power n, what we're going to guess is, first we're going to start off with power 1, x minus a, then we're going to do, so a1, and then we're going to do an a2 over x minus a squared, all the way up to the highest power that happened for the n. So if we had a cubed, I would do a1 over x minus a to the power 1, plus a2 over x minus a squared, plus a3 over x minus a cubed. I would stop at the last one. So this is the guess that we make for each power. These are the linear ones. So those are the linear factors. They're going to be multiplied all together in that denominator of b when we factor it. And then instead of having them all multiplied together, we now get this string of pluses when we can integrate. The idea is we're trying to integrate. So I'm splitting the products into these individual sums, which we'll have a technique to integrate all of these in a second. And now what happens if you have an irreducible quadratic? So 3, if we have 1 over x squared plus a squared, what do? Notice that the square's been completed already. So if you get the worst case scenario, you're going to have to complete the square first. But we guess this is quadratic. In the first one, it was linear. So we did degree 0 polynomial over degree 1 to keep it proper. So this is quadratic. So we're going to guess a linear polynomial over our quadratic. And then if in the worst case scenario, we have something 1 over x squared plus a squared to the power m now. This is the worst case scenario that I was talking about in partial fractions. And that implies we're going to use trig substitution for that one. And what are we going to guess though? We're going to guess a1x plus b1 over x squared plus a squared plus all the way up to amx plus bm over x squared plus a squared to the power m. The same thing as the linear ones, but now we just have the irreducible all the way up to the largest power that appears. So those are our guesses for partial fraction decomposition. So as a baby example of doing this, if I have x squared plus 1 over, say, x times x minus 1 squared plus x squared plus 1 times x squared plus 4 squared, or let's do a cubed. Let's do this one squared. If this is my a of x over b of x, the first thing in partial fractions is you have to make sure, and I've already done it for us, I factored the denominator. I don't care about the top, whether it is or not, because I could do -1 even, I don't care. That'll be the next part. There's a cat sitting on the chair right next to me. So what do I do with this now? I have to make my guesses. So I can ignore the top. I have x minus 1 cubed, x squared plus 1, x squared plus 4 squared. So the 1 over x implies, I guess, a over x. the 1 over x minus 1 cubed means that I'm going to guess I have to keep using different letters or start indexing them. I'm going to use b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. You go up to the highest power, you stop wherever that power was. I also have a 1 over x squared plus 1. That means I'm going to guess ex plus f over x squared plus 1. And then for the last one, I have 1 over x squared plus 4 squared. Now I'm going to have to guess gx plus h over I'm just keeping going through the alphabet. These are all just numbers that we're going to find eventually too, over x squared plus 4, and then plus ix plus j over x squared plus 4 squared. And then again, it's because I had the power 2. That's when I stop. So if it's irreducible quadratic, you do linear terms over those powers until you get to the highest power that you had. If it's a linear one, you do the same thing till you get to the highest power, the 3 or the 2. So these are the guesses. And you can eventually tell how many of these coefficients you're going to have to find horribly based on the degree of my polynomial. The degree on the bottom is 1, 4, 5, 6, 7. So, oh no, wait, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The degree is 10, so I should have 10 coefficients. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to J. J happens to be the 10th letter in the alphabet, it turns out. So I know how many variables I'm going to have to find based on what the degree of the denominator b is. The degree of b is 10. Implies 10 coefficients a, b, to j. Those are the letters of my initials. But this is the idea. So on an exam, especially too, it's not a mistake that I'm being mean. Well, I know exactly how big of, and this is where linear algebra is going to come into 115, math 120, because we have to solve a system of linear equations this is 10 equations and 10 unknowns. I don't want to do that without linear algebra. I won't give you that big of one on exams, but on the assignments and stuff like that, this is going to be the hard part. On top of everything else that's crazy about partial fraction decomposition, we're also going to have to solve linear systems in this scenario. So you make your guesses, is what we do, is the moral of the story. Or my step by steps I have. So once I've made sure it's rational, then I factor the denominator, then I make my guesses. Then what do we do with these guesses? Once we have the guesses, now that we have our partial fraction guesses, what we're going to do is we have to find the unknowns. We have to find these using linear algebra. That's the technique we're going to use eventually when I set up the equation, by setting the numerators now equal to each other. What do we mean by that? So, as an example, what I want to do with this, let's do something like, if I have 5x minus 3 over this guy. Well, then first of all, the first step is it proper? Is what you just want to start running through. Yes, the degree of the top is 1, the degree on the denominator is 2, so this is proper. Is the bottom factored? No. So that's my next step, factor it. Now it's factored. So is it proper? Yes. Is it factored? Yes. Now you say I have to make my guesses based on the denominator. I have 2 linear factors. So the 1 over x plus 1 means that I'm going to guess a over x plus 1. And the 1 over x plus 3, some of the books will write it because I have the product of that, means that I'm going to guess b over x plus 3. So this says that we're going to guess that 5x minus 3 is equal to x plus 1, x minus 3, or sorry, it should be x. Yeah, that's it. And then we're going to guess that that is equal to this guy. So the first thing you need to do is get a common denominator. This is the common denominator. So what am I missing here? X minus 3, so I multiply by x minus 3. What am I missing here? X plus 1, so I multiply by x plus 1 in the form of 1, x plus 1 over x plus 1. Now I have a common denominator. Now I can focus on the top, and that's what it's saying. Now that I find a common denominator, I have to solve for a and b in this system by comparing the numerators to each other and seeing if those polynomials are equal. So now what we're going to get is that says that this polynomial, 5x minus 3, has to equal ax minus 3 plus bx plus 1. So group everything together. That says 5x minus 3 has to equal a plus bx plus, or sorry, minus 3a plus b. So now what we're doing is we're matching the coefficients, the x power and the constant power. So that gives me equations in each of the powers. When are 2 polynomials equal? If and only if all the coefficients are equal. So in the x1 and the x to the 0, that's when I have 2 equations. In the first one, it says a plus b has to equal 5. The coefficient in front of the x's have to be the same. So that says a plus b has to equal 5. That's where I'm getting the equation from. And now in the constants, it says that negative 3a plus b has to equal negative 3. And now you can see this is why I was saying this is essentially linear algebra. If you know what I'm talking about, we just got an augmented matrix of negative 3, 1, negative 3. Math 120. I have videos up on YouTube if you really want to watch, but if it's 2 by 2 or 3 by 3, usually they're going to give it where you just plug in the equations. I can use from the first one, I know that b is equal to 5 minus a. And then I plug that into here. So that says that negative 3a plus what was b? 5 minus a is equal to negative 3. So that says negative 4a is equal to negative 8, or a is equal to 2. Yeah. What does that make b? Well, then b is 5 minus 2, which is 3. So I've now got my coefficients. So on top of this, this is why on top of every other integration technique that we give, you're going to like this one even less, because now you have to do linear algebra inside this. In this step, you have to use linear algebra to find your unknowns a and b. Once I have them, now what that says is 5x minus 3 over x plus 1, x minus 3 is equal to what was a? A was 2 over x plus 1 plus 3 over x minus 3. And now if I want to integrate that thing, we're off to the races. The integral of 5x minus 3 is x minus plus 1, x minus 3 equal dx. The whole point of that crazy story that I just gave you in hyperspeed, because it's the last class before our long weekend, was I have this proper factored rational function. I want to integrate it. So the first two steps are make sure it's proper and make sure it's factored. Once I do that, it's ready to do your partial fraction decomposition guess. You make your guesses. You solve for the unknowns, which we just did for this specific one. And now let's have in the denominator, when I had the products of these powers, linear factors or irreducible quadratics, I can now write it as the string of integrals of, and it doesn't care about the constants. So 2 over x plus 1 dx plus 3 integral of 1 over x minus 3 dx. And these integrals should be Pavlovian, or use the baby substitution if you have to, but these are 1 over x essentially, which is natural logarithm. So this is going to be 2 the natural log of the absolute value of x plus 1 plus 3 times the natural log of the absolute value of x minus 3 plus c. And then in the back of the book, what they're going to do is they're going to write this as natural log of x plus 1 squared. The number on the outside becomes exponent on the inside, plus the natural log of the absolute value of x minus 3 cubed. Notice I had to keep the absolute value on the second one because cube doesn't kill the negative. And then sum on the inside is product on the, or sum on the outside is product on the inside. So this is natural log of the absolute value of x plus 1 squared, x minus 3 cubed plus c. They always like to write it as a single natural logarithm if they can. But you didn't really have to do that. So the last thing you do, so hence, once we have found the coefficients A, B, C essentially for our guesses, we can integrate where possible. This is not easy. In the worst case scenario is the irreducible quadratic to the power. We're going to have to use trigonometric substitution even to get ourselves out. So, like, why is the other laptop's not plugged in? I'm like, why is it dying? I think I just killed. Did I kill it? Where? It's old. It doesn't stay unplugged for very long. Apparently, an hour and a half, and it dies. But I guess I'll just wing it while it reboots. Partial fraction decomposition. That's not quite the story either, because factoring is not easy. That game's not, and I kind of washed over that. And then based on the types of integrals you get, once you've done all this and separated everything into terms, there's still, you need to know how to integrate really fast all of these different guys. And so once we do this correctly, because it's going to be proper rational functions, every single thing that I integrate or do this with should be, once we integrate, it's either going to be a polynomial, the power rule, or a natural logarithm, or arctangent, based on how we decompose our partial fraction decomposition. So let me just go back to this partial fractions. And then, so yeah, I should go through all these cases. Okay. First of all, what are the steps? 1, make sure it's proper. If not, use long division. And then you'll get something that you'll have a polynomial plus a proper rational function. 2, factor the denominator. You're focusing on the bottom right now, not the top. B of x into linear terms, linear factors. And irreducible quadratics. Once you do that, then 3, what are you going to do? You're going to make your partial fraction guesses. Once you do that, 4, what are you going to have to do? You're going to have to solve the linear system. By matching the coefficients to find the A's and B's. And then we can integrate. If you dare. This is still not going to be easy. So in the last 3 minutes, what are the types of things that we're going to have to, I can't even go through an entire one, but this will get us through at least. If you look at my multivariable calculus one, I might have added it too, but at the end, there's an appendix where I do a partial fraction decomposition. I have like a 30-minute video somewhere on my YouTube channel. I think it's under the multivariable calculus. They were like, when I was doing multivariable calculus, when we're doing triple integrals. And I'm like, I can't remember how to do this. And now you're making me do it with 3 variables. So I went over partial fraction decomposition. But the last example I'm going to do is integrate each. These are the types of things that you're going to get all the different scenarios once you have made your partial fraction decomposition and found all the numbers. So 1, you may have to do the integral of 7 over, say, x minus 1 dx. You might get something that looks like that. You find a is 7, and then you had a linear term. Or you might have had a power of that linear term. What is 7 over x minus 1 cubed dx? You might get a term that has a power in it. Eventually, you've separated them all out, and then you're going to have to integrate these individual terms. Something might look like that. And then 3. I won't get to them all today. I'm just going to list them. This is what you can start practicing over the break, is partial fraction decomposition and then a Weierstrass substitution a little bit. And then I'll continue once we're done after 9 days of being off. You also might get like a 2. Let's not even make it a 2. That's not right. Let's just keep it a 7. What if you get 2x over x squared plus 1, an irreducible quadratic? You might have to deal with that thing. Or what happens if I get just an irreducible quadratic? 5, the almost worst case scenario. What if I get, this is supposed to be a 7 over, oh, what if I throw that extra x on the bottom with that guy, dx? That's irreducible, but now he's not completed square. You got to complete the square on that guy and then do our arctangent business. And then the worst case scenario is going to be the integral. Well, you might have something that has 7x over x squared plus 1, say, to the power 2 dx. That one's okay. And the worst case scenario is going to be the integral where you don't have that, the x. So this is worst case scenario. And we use trig substitution because we can let x equal tan theta. But when we're going through, this is going to be, just as we start, natural logarithm. That one's done. What's this one? we could just read off a few of them. This one's going to take some work. This one's just the power rule. This is equal to the integral of 7 x minus 1 to the negative 3 dx power rule. That one's easier, even easier. This one is substitution. And then you're going to get natural logarithms. This one is arctangent. This one is complete square. And then arctangent. This one is substitution. And then the power rule. And then this one is trigonometric substitution. Is the worst case scenario. So there's the techniques of what I didn't actually compute all the integrals because I got to go. I got 2 more classes today. A bunch of crap to do. It's like nothing like leaving everything just before. I want to get all my stuff done before the reading break. But those are, once you decompose, regardless of whatever horrible proper rational function they gave you, this now gives us a way of splitting it into those terms, making all the guesses. Once I have all the guesses for the numbers, then I have just an integral, which was the product. I've strung it into a bunch of these strings. I can now, these are the types of terms that you're going to get. These 7 integrals represent the 7 different types of things that you're going to get in each time. But this is what I say every time I say it. You're another new class. That's probably the first time you heard me say it. But when I rant about partial fraction decomposition, you're doing something wrong if your antiderivatives at the end aren't the power rule, natural logarithms, or arctangents. The only thing I'm going to get are the power rule, natural logarithms, and arctangent, except for the worst case scenario where I make a trigonometric substitution. But in the other 6, I got natural logarithms, or power rule, or substitution and natural logarithms, or arctangent, or power rule. Everything is the power rule, natural logarithms, or substitution. Once I correctly take a rational function, make it proper, back to the denominator, make my partial fraction guesses, find the coefficients, then integrate. Have a good long weekend. I'll see you the Tuesday after.